Thank you so much. It's a great honor to be here, to look out and see so many old and new friends. So I'm going to talk about why quantum observers find lower entropy, both after observation and also in our early universe. Now, one of the things I love about being here is that this is a crowd where there's such a great degree of openness and friendliness. Debating the interpretation of quantum mechanics usually looks like this, as opposed to debating the second law of thermodynamics, which usually looks like that. And I'm going to talk about both of these here. And I noticed you're just laughing instead of hissing, and which is what I think is so great about what the organizers have put together here. So there are these two century-old controversies: how to understand quantum mechanics and how to understand the second law of thermodynamics. And I'm going to argue in this talk that both of these great controversies are actually linked, and that they can be resolved in the same way. It's a pleasure being here in Cambridge to get to quote Arthur Eddington, who said famously that the law that entropy always basically said that, the second law of thermodynamics is the supreme one out of all the laws of nature. You see, he says here, if someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, well, then so much the worse for Maxwell's equations. If it's found to be contradicted by observations, well, those experimentalists do screw things up sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. So that's the pro position. But on the other hand, there has been a lot of serious objections also to the second law, going as far back as Maxwell, Gibbs, Schmidt, and Poincaré. And there's still really no consensus about it. And I'll come back and explain a bit what the controversies are about there. So in summary, I'm arguing that the quantum measurement problem, the cosmological entropy problem, and also the inflationary one ultimately have the same solution. So let's first just review a little bit what the problems are, and then let's explore this solution that I think that they have. So the measurement problem, of course, is that the way quantum mechanics is taught in most textbooks still today is either logically inconsistent or incomplete, meaning that it's unable to make predictions for certain experiments. Because we're told in these textbooks that one, all isolated systems evolve according to the Schrödinger equation, and two, that sometimes they don't. Because when they're observed, then the wave function collapses in a sort of random way, and all the textbooks we use when we teach quantum mechanics at MIT fail to give any kind of equation for exactly when item 1 here is supposed to be violated, when the collapse is supposed to happen. So Hugh Everett, of course, famously in 1957, proposed a radical solution to this, which is just scrap the second part and say there is no wave function collapse, and say Schrödinger equation always holds, period. Now, one fascinating sociological thing I've learned over the years is that there are actually many different interpretations of the Everett interpretation. And there are also many different interpretations of the Copenhagen interpretation. So whenever I get people arguing, I usually try to pin them down to write down which one they mean, and then they start arguing amongst themselves. I'm not so interested in these kind of many words controversies as opposed to many worlds controversies. You're welcome to define things whatever way you want. I'm just going to specify what I mean. So what I mean by what I'm going to talk about here is just to say the Schrödinger equation holds always, period, no exceptions. There's no more metaphysical baggage or anything like that I'm attaching to this. Just that. So what I personally think is founded on these two basic hypotheses, which will underlie everything I say in the talk today. One is what I like to call the external reality hypothesis, saying that there exists an external physical reality, which is completely independent of us humans. In other words, I think that if there's a civilization having another physics conference now in the Andromeda Galaxy, they would happily exist and keep having their conference just fine, even if our politicians on this planet screwed up and we all went extinct. I think physical reality doesn't hinge on us existing. This is controversial. You know, Niels Bohr famously said, no reality without observation, which you could argue, if you want, violates this, because it sort of puts us, it says one can't talk about reality existing without having us in it somehow. So this is a non-trivial assumption. And the second thing I assume is what I call the no secret sauce hypothesis. Many people think of consciousness as something mysterious that can only exist in biological organisms such as us. I really don't like this carbon chauvinism, the assumption that you have to be made of carbon atoms to have subjective experience. I'm a physicist. I think that we are our particles, and consciousness is just the way information feels when it's being processed in certain ways. So I'm going to, throughout this talk about observers as just physical systems, a particular kind of physical systems, nothing more. All right? So what about the entropy problem? Well, there are actually two separate entropy problems that are really fun and interesting, right? One of them is that this sometimes happens when I try to cook, but I never see the opposite happen, and people have for a very long time pointed out that it's kind of weird that on one hand, the microphysical laws of physics are reversible with respect to time, but the second law of dynamics is not. So as entropy increases, it doesn't decrease. So how do we resolve that? It's very well known by now that if you make the assumption that the entropy right now is for some weird reason extremely low compared to thermal equilibrium, then one can derive that we will tend to see entropy increasing. But that doesn't fully answer the question of why we see an arrow of time today, of course. We say that the arrow of time exists because the entropy is low. Why is it so low? Because it was even lower yesterday. Why was it so low yesterday? Because it was even lower the day before that, and so on. So what we have learned is that the ultimate explanation of the arrow of time has something to do with the early universe, which is kind of shocking. But then we still have to explain why was our early universe entropy so low, which is the second entropy problem. The usual answer people give is they wave their hand and say inflation. But as we'll come back to in detail, that per se is not enough. And Sean Carroll, for example, has even written some really nice work showing that it's not that easy. After all, inflation itself is just a physical process, right? So if we have a Hamiltonian evolution of the density matrix, its entropy will stay the same. Why would it be lower than after inflation? All right, so enough about problems. Let's talk a bit, to inject some hope in this and talk about solutions. My basic theme is that we must not ignore the subject. You must not ignore the observer. I feel that for many years we physicists have really been very queasy about talking observers because it felt sort of almost taboo to talk about anything that sounded like consciousness and philosophy, and we didn't want to talk about it. But that puts us in a really weird situation, because physics is the science of observing the world, right? And yet we're refusing to try to be rigorous about the observer. And I think, in fact, our hesitancy to talk about the observer has caused us a lot of problems. We know that we still have failed to unify quantum mechanics with general relativity. Well, maybe it has something to do with the fact that these two theories have exactly diametrically opposite views of what an observer is. In general relativity, an observer is this infinitesimally tiny, massless object that has no effect whatsoever on the rest, right? Whereas in quantum mechanics, it's very different. The observer can really affect what is being observed. So I want to just, since I'm making the no secret sauce hypothesis, that the observer is just part of our universe, it's a physical system, I want to talk about it explicitly. Richard Feynman famously said that it's convenient to divide our whole system into two parts. the thing you're interested in, the object, and the environment. And as we know, if you partial trace out the environment, you get decoherence and all sorts of interesting processes you can study. In this spirit, I want to divide it not into two, but divide the entire universe into three pieces. The object that we're interested in, it could be your Stern-Gerlach apparatus or anything you're studying. It can be the environment, which is everything else that you're not interested in but that exists. And finally, the subject itself, you, or the degrees of freedom of your brain that are having the experience. Okay. If we have a Hamiltonian, that describes our whole universe, then if we divide it up like this to describe, then what's going to happen, we can write the Hamiltonian as a sum of a bunch of different terms. One term that describes just the internal dynamics of the subject, the object, and the environment, and then interactions between them, pairwise and three-way interactions. Now, I think that consciousness is just the way information feels when it's being processed by certain physical systems, when it's being processed in certain complex ways, no secret sauce, as I said. And with this perspective, then, these different interactions actually give rise to a lot of very interesting effects. The internal dynamics of the object, that's just the usual causal evolution of the system that you're looking at. That's usually the first thing we do in quantum mechanics 101 when we teach it, right? When the object interacts with the environment, that gives us decoherence, as we know, which will typically increase the entropy of the object. So I'll come back and talk about. When the object interacts with the subject, on the other hand, that's what we call measurement. And from what Everett argued in his work was that it's this process which, when you analyze it carefully, gives rise to the illusion of wave function collapse. And finally, there will also be decoherence directly on the subject, which we can talk more about. Thinking about it this way is very, very linked to entropy, because when the object is just interacting with itself, the entropy of the object will stay the same, because it's just unitary evolution. When the object interacts, when you're not looking at the object and it's just interacting with the environment, its entropy increases, like in the traditional second law. But when you are looking at the object, when you're observing it, interacting with it, its entropy will typically decrease, as we'll get back to. So just like the second law of thermodynamics should have a twin law that goes with it. Law one is entropy increases from this interaction, object-environment, and it decreases from subject-object interaction, typically. This may seem very intuitive, but it is controversial. For example, my friend David Albert said at the conference we organized not too long ago that thinking about that entropy has anything to do with what we know about a system is a bad, misleading mistake. All right? But I disagree with that. I'm interested in using physics to make predictions about my own future. And for that, actually knowing the full quantum state of the whole reality that exists, the density matrix, sort of with a capital T, is actually not enough. And it's also not necessary. There is a particular density matrix, however, which summarizes everything that's relevant to me, that I can know about the object. And to get from the full density matrix of everything, the full density matrix of all three of these things taken together here, to just mine, there are two mathematical steps I have to take. I have to partial trace out everything that I'm not interested in, everything that's not in my subject, my object rather. And I also have to condition on what it is that I already know as an observer. And I'll come back and explain what I mean by that a little bit. So in other words, it's not enough for me to just use the full density matrix of everything, because I need to know something about where I am. If I want to predict what I'm going to see when I open my eyes, I have to know where am I in space. Am I here in the Andromeda Galaxy or whatever? I need to know where I am in Hilbert space also. If there's a big Hilbert space with a superposition of Max being here and Max having overslept and missed his flight and still being stuck in North America, I need to know that too. I need to condition on these things to get the right prediction. And second, it's not necessary for me to know the density matrix of everything. It's perfectly fine to partial trace out the things that I'm not interested in. That was the beauty of von Neumann's invention of the density matrix, that you can actually choose to ignore all these things you don't care about. So in other words, we have to be very careful and avoid loose talk of the density matrix, because when you think about things in this way that I'm advocating, we each have our own personal density matrix, which describes our knowledge about the object, and to get from the full density matrix to that, there are these two mathematical operations that I just mentioned that we need to perform. There is the process of observation, whereby we condition on the things that we have observed. And I'll come back to what these formulas are. But this is just mathematically what actually happens when you go from the full density matrix to ours. And then there's the partial tracing over the environment. And I'll give you I'm going to show you two actually rigorous theorems that we've proven with entropy inequalities, which generalize the second law of thermodynamics, showing that how decoherence increases the entropy and observation on average decreases it. And just to re-emphasize this very important point of why we have to be careful to not loosely talk about the entropy or the density matrix as if there is one single the entropy of the density matrix. If you have a very messy wave function, if you have inflation with quantum fluctuations, etc., and you end up with a quantum superposition of a universe expanding this way, a universe expanding that way, and in one branch of this, our solar system has 8 planets, and some other branch of the wave function, our solar system has 9 planets, and some it has 42 planets, and some other branch, well, inflation didn't end so well, and we didn't get any galaxies at all. If this is the full quantum state, right, and we're interested in making predictions for what we should observe, first of all, we should condition on them the fact that we already know that, hey, we are in a place where there are galaxies, and in fact, we know a whole bunch of stuff. We condition on that, and most of this stuff then becomes irrelevant to the density matrix we care about. And then we partial trace about things that we're not interested in. Okay, let's drill down a little bit deeper now into the interaction between the subject and the object. So talk about entropy and observation. So in classical physics, first of all, as we learned from Shannon, we can use entropy just as a measurement of our ignorance. So for example, if I have a playing card here, and I know that it's a king or a queen, but nothing else, I can write down a probability distribution for what it is. It's going to be a uniform distribution with 8 possibilities. I can calculate the entropy by Shannon's formula. It's 3 bits. If I now make an observation and I get some information saying actually it's a queen, right now there are only 4 possibilities left. The entropy reduced by 1 bit is 2 bits. What did I mean when I say the entropy? Well, remember, I'm talking about the entropy of my description of this system, right? So in my description now, the probability distribution has changed because I got this new information. I can use Bayes' theorem. It went down, it decreased. Entropy decreases from observation, exactly the opposite of the traditional second law. Now, suppose I find out it's a black card. Now, entropy went down again by 1 bit down. So there's only 1 bit left. Now I observe the card by turning it over. Now it went down from 1 bit to 0 bits. Von Neumann showed how we can generalize this very nicely to quantum mechanics by replacing the probability distribution of classical physics by the density matrix. Now things are a little bit more fun because you can have off-diagonal elements in this. So the entropy will be 1 bit if I have no off-diagonal elements. The card is, the particle says here or there, I just don't know which. Whereas if you have this off-diagonal element, you can think of it as being here and there in a quantum superposition at the same time. And entropy will be 0 bits because you can do a unitary transformation where, in fact, probability is 1 that it's in a certain quantum state. So in summary, how do you lower entropy? Basically, the entropy of something decreases when you look at it, whereas it will typically increase when you don't look at it from decoherence. Okay? So let's talk a little bit more about decoherence. That's now going to be the interaction instead between the object and the environment. And let's talk not just about decoherence, but also about how all three of these kinds of processes interact with each other. So first, let's just do a little bit of unitary evolution. So just the object itself interacting under its own dynamics. If I have a playing card that has a perfectly sharp bottom edge, I balance it exactly on its tip. According to classical physics, it'll stay balanced forever, right? But we all know, according to quantum mechanics, it'll actually fall down in under half a minute. The famous homework problem we give to our students. It will fall down left and right in a quantum superposition. So the density matrix will look something like on the left here. And then if some air molecules bounce off of this card or some photons bounce off of this card, we get decoherence. When we partial trace over this environment of the air molecules or the photons, the off-diagonal elements go away, and the entropy has now increased by 1 bit. The fallen card was in both places 0 bits, now it's 1 bit. If we do this with mathematical notation, it's all very standard stuff, nothing to dwell on, the off-diagonal elements of the density matrix go away. What counts as an observer? Einstein famously asked if a mouse could collapse the wave function by looking. From this perspective, what counts? A human, a mouse, a robot, a photon? The answer is all of the above. It's just the information transfer that matters. As soon as the environment finds out about the information, and you partial trace over it, boom, decoherence happens, entropy goes up. It doesn't matter if the observer is conscious. It just has to be able to record information. And an easy way to see it is with this example. Like suppose I have a mirror, and it's in a superposition of being in 2 places, either position A or position B. If that's the object, entropy is 0 bits, because it's a coherent superposition. If I bounce a photon off of it, depending on where the mirror is, the photon will be in 2 different places a short time later, because either it will be here or it'll be here, right? So by just looking at the photon, you could have figured out where the mirror was. The information about the mirror has leaked into the information about the photon. If you don't observe the photon anymore and you partial trace it out, entropy has gone up by 1 bit. So anything can be an observer as long as it can record the information. Now, how much time do I have left? I'm going to make an observation of the chairman.
14 minutes?
14 minutes.
Can you define record?
Yeah, I don't mean that the photon has to actually do anything to like write it down on its photon notepad or anything like that. I just mean that the information itself is contained already in the photon system. So a clever experimentalist could, by measuring the photon, extract the information.
To change its quantum state irreversibly, or is it a fourth language, or not?
Well, no, don't need to assume anything. I'm just saying, if the photon is here, if you know that, if you can measure that, that means that the mirror must have been here.
No, but measure that means that you actually have a irreversible detection.
Yeah, later on, yeah. That's right, exactly. Exactly. I won't dwell on the details of decoherence very much. It's a very well understood subject. Now, since it's amazing, since Hans-Dieter Zeh first, we worked these things out around 1970, and how much, and Wojtek Jurek and others, many of you who are here, have how established this has been and has become. And I just want to emphasize one thing, which is it's really striking how fast decoherence is. It's really the fastest process in nature. If you compare this decoherence with dissipation, which are 2 different things that happen when your object interacts with its environment, dissipation involves the transfer of energy between your system and your environment. So to change the energy of your system a lot, if it has n particles, you have to basically bounce off of order n particles or transfer n little, you have it. Whereas for decoherence, if you just want to find out where the thing is, you only need one collision, not of order n of them. Right? So if decoherence can be Avogadro's number faster. It's an incredibly fast process. And for things that we call classical systems, then you want to have the dynamical timescale to be much shorter than the dissipation timescale so that they're actually exhibiting some form of independence, but much longer than the decoherence timescale. I worked out long ago what the decoherence timescale is for a lot of different systems, and I don't know if Stuart Hameroff, are you here?
I'm here.
Yeah, so Stuart Hameroff got upset with me because I worked out the decoherence timescale for neurons, and we'll probably discuss this more tomorrow. Whereas I claim that the decoherence timescale for neurons in your brain is 10 to the minus 21 seconds. And maybe Stuart can think many thoughts in 10 to the minus 21 seconds and have quantum processing going on with his neural network, but I can't think that fast, especially not when I'm jet lagged. Decoherence really helps us understand a lot of fascinating things about the emergence of a classical world. Here are some results that I've never gotten around to actually publishing, so I'll share them with you anyway, just for fun, so that someone can hear about them. I worked out how decoherence causes space-time itself to be classical. Because if you have a region of space, which is in the quantum superposition of having this metric or that metric, suppose you have some gravitational wave, which is here or not here, for example, then any kind of particle that flies through this space will end up getting entangled with this, and because where it comes, it's going to be in two different places when it came out, depending on what the space was, and you can then partial trace over this. And what's kind of fun is the math that I got from doing this is exactly analogous to what happens when you go and get an MRI in the hospital. It's well known that by sending particles through your brain in many different angles, you can do the inverse radon transform and reconstruct the full three-dimensional structure of your brain. Well, in that same sense, decoherence is by just sending particles through in all directions, reconstructing the full three-dimensional metric, which means it's decohering it. And here's a little plot summarizing all sorts of different kinds of particles, how they decohere a space. Turns out that the cosmic microwave background does a pretty good job of decohering our space, but the cosmic neutrino background is even better. Because these neutrinos, they have very low mass, but they're not zero mass. So they have a very short de Broglie wavelength, which means that they make space, for all practical purposes, classical above this length scale here. So experiments, even very precise ones like LIGO, that got the Nobel Prize here, are detecting, actually, we predict from this, a very classical space. And to see truly quantum things, since you can't get away from these pesky background neutrinos.
And that's only for the exact tube that they pass through, not the vicinity.
Well, but the thing is, over a period of time, they can tend to pass through everywhere. That's the beauty of them. And if you look at, this also helps, I feel, with this very old question about when you do quantum gravity. We don't have a theory of quantum gravity, of course, so what we love to do is just say, well, and when we do general relativity anyway, instead of using the stress energy tensor, which is a quantum thing now, we just take the expectation value and hope that's okay. That is okay precisely when you're above this line, so that decoherence is making your space classical. But if you go below that line, it's not okay. So to come back to how these different things interplay with each other, if you have this playing card it's going to fall down. If I've bet $100 on that it's going to fall down one way and not the other, first it falls down, I still have my eyes closed, so I don't know if I'm going to be happy or sad. But the card is in a coherent superposition, the object. Now I open my eyes, there's an interaction between me, the subject, and the card, the object. I get either happy or sad, or happy and sad in a quantum superposition. So effectively, Everett would describe this as there being effectively two parallel universes that decoherence prevents from interacting with each other. If you geek out on this and just look at how the density matrix evolves, what's happening here is first step for the card, right? It's still in a pure state, superposition now of the two ways it's fallen, and then if it interacts with the environment first, then decohered, and then I observe. But you could also have done it the other way around. It could interact with me first, and then decohere, and in the end you get the same thing, and everything works out. The part about what happens to the density matrix mathematically when it decoheres is very well understood, and for most cases you just suppress the off-diagonal elements in it. The part that happens when you instead look at it, when we work this out, I like to call this formula the quantum Bayes theorem, because it is precisely Bayes' theorem. Again, Bayes' theorem tells you classically, if you have a probability distribution for what your object is doing, right, and then you observe something about it, it tells you how to update your state of knowledge of it. In this case, the state of knowledge you have is your density matrix, so this tells you how to update that. And so I got very interested in whether one can prove something a bit more rigorously here to sharpen the second law a little bit. Instead of just saying the second law of thermodynamics is that the entropy cannot decrease, it would be nice to show something rigorous about exactly what decoherence does to the entropy and what observation does to it. And qualitatively, what you would hope to be able to prove is the following: that first, the object's entropy cannot decrease unless it interacts with the subject. So that would be the standard second law, right? And then the opposite version as well, which is that the object's entropy cannot increase unless it interacts with the environment. So that it's only decoherence that can do that. So so mathematically, when you take an arbitrary interaction with the environment through decoherence, what we're actually doing with the density matrix is taking a Schur product of it with a positive definite matrix like this. So, which means you just take your density matrix and you take this other matrix, E, and you put it one on top of the other and just multiply all the numbers pointwise. And there's a very nice theorem I found from 1985 by Bapat and Sunder, which lets you prove that the eigenvalues of a matrix, rho, majorizes the eigenvalues of the Schur product of rho with E. And if you don't know what majorization is, you're not going to learn it here unless you catch me in coffee break, because I think I'm almost out of time, right? How much time is there left?
1 minute.
Okay, perfect. So you definitely won't hear it here. And it's also well known that majorization is directly linked to whether entropy increases or decreases. So that's why this paper here that I wrote has a rigorous proof of that. The other part is a lot harder to prove, that the entropy will decrease when you look at things. In fact, it only decreases on average, but that it does. And so I wrote this. That part, I was stuck on this key mathematical part until this wonderful student, Hrant, who's now a grad student at Stanford, he was at MIT then, helped me with this, and together we geeked out in a big way, and the end of all this math was this very nice theorem in the box here, which is very easy to remember just with words. It's exactly like you would hope, that on average when you look at something, its entropy will always increase if you learn something about it. And to just summarize all of this, what does it mean when you observe things? You could actually take a number of different increasingly strict definitions of what you mean by observation. And depending on what definitions you pick, you get either more theorems or less theorems, okay? If you define observation just as von Neumann reduction, so that the density, so that your, or so that you actually see at the end of it your object in a definite state, then it's always true what I said, that observation will decrease the entropy if you learn something. The more general thing of Luder's projection, it also works. And if you take a slightly looser definition of, or actually much broader definition of interaction, of this interaction, which we call probing in our paper, which basically means that you learn something about the system without messing with it. You can still prove rigorously both of these parts of the quantum second law. That if you want to be still more general and look only at purity preserving POVMs, you can still prove that observation decreases entropy, but you can no longer prove that that decoherence increases it. And if you go maximally general and just look at arbitrary POVMs, you can't prove any of these theorems anymore, and we actually get counterexamples for them. I'm out of time, so what you can ask me about in the Q&A if you want is how come you can observe, how come you can make entropy not just a little bit lower by looking at things. Now, typically you would expect if you observe something and you gather 5 bits of information about it, you reduce its entropy by 5 bits. So how on earth can you then, by looking out into the universe, reduce its entropy by maybe 10 to the 80 bits, even if you just observed a few bits yourself? Amazingly, it turns out that if you have inflation first, that's exactly what happens. Inflation has this magical property that it causes very, very long-range correlations between what's out there. So a very crude toy inflation, which captures exactly this idea, is suppose you just think of all parts of space here. Green means parts that have inflated, and red means don't. Okay, so whenever inflation starts somewhere, it goes exponentially and inflates a really, really large patch. There's a very, very strong correlation between whether one pixel has inflated and whether the neighbors have inflated. And if you start just observing, if in a random place, oh, this Planck volume here has inflated, or this volume here next to it has also inflated. This is also. If you observe, say, 100 little volumes and they've all inflated, the probability is now 2 to the minus 100 that you're in this messy non-inflating region. So even though you only observed 100 bits, I'm going to spare you the details. But if you plot basically what the entropy is of the rest of the world now, your object, versus how much you observe, if there's been inflation, it drops exponentially with how many bits you measure. Whereas in a typical situation where there hasn't been inflation, you only reduce the entropy by the red line, by the amount that you have observed. So this is how I feel that inflation actually helps explain why our early universe had such low entropy. It doesn't do it alone, but when you combine it with these quantum ideas that we've spoken of, then it actually works beautifully. So I'm just going to summarize here and saying that I think if you actually put the observer back center stage as the subject and split the total physical system that is our reality into 3 parts, it nicely unifies all of these things to do with observation and thermodynamics. And here is the summary of the math that's relevant. How decoherence, which is an interaction between the object and the environment, increases entropy, and how the measurement, which is the interaction between the subject and the object, decreases the entropy. Thank you.